Hello everyone, I hope that you are all doing well. My name is Richard, and for this week's presentation, I'm going to be deriving the Michaelis-Menten equation. So there are four equations here that we are given that we're going to be referring to later. And this is the starting point and first step that is already given to us here. So why don't we go over this top portion here, as it is the foundation of the equation itself. So we have an enzyme and a substrate, E and S, going to make the ES, or enzyme substrate complex, and that goes to make enzyme and product. So you can see here that the enzyme substrate complex can go in two directions. You can either go back and form enzyme and substrate, or you can go forward and make product. So these variables that are up here, K1 is the formation of the enzyme substrate from E and S. K minus 1 is the formation of enzyme plus substrate from the enzyme substrate complex. And K2 is the formation of the product from enzyme substrate. So now we can use the steady state approximation, which basically states that the creation of the enzyme substrate complex is equal to the sum of all of the reactions that are decreasing its concentration. In other words, we can say that K1 minus K negative 1 minus K2 is equal to 0. Or K1, remember that K1 makes the enzyme substrate complex, K minus 1 consumes the enzyme substrate complex, and so does K sub 2 does the same as well, consumes enzyme substrate complex. So now we can use this equation that's given to us. This basically lets us know that the instantaneous change of the enzyme substrate complex over time, dEs over dt, is equal to 0, and it's equal to K sub 1 times E times S minus K negative 1 times ES minus K2 times ES. And this basically is letting us know that the reaction rate only depends on the concentration of the reactants. So as you can see over here, for K1, the reactants are the enzyme plus the substrate, which forms the enzyme substrate complex. For K minus 1, the substrate is the enzyme substrate complex itself, because the products are the enzyme plus the substrate. Okay, so at this point, it's difficult for us to determine the value of the unbounded enzyme E, so we define a new variable here. So the concentration of total enzyme, or E sub t, is equal to the concentration of enzyme plus the concentration of the enzyme substrate complex. So if we solve for the concentration of E, like so, just rewrite the equation. Concentration of E is equal to ET minus concentration ES. So now we can plug in this value of E over here, and I will be doing it on this page here. So we're going to move this up here. So down here, it's going to get a little messy. So we have 0 equals K1, and we're going to plug that new value of E over here, times E total minus concentration of ES in parentheses here, times concentration of S, minus K negative 1 times ES minus K2 ES. So all I did from here to here is plug in this value of concentration of E over here. So that's all here. So now if we distribute the K1 and the S, we are left with 0 equals K1 times ET times S minus K1 times ES times S minus K negative 1 ES minus K2 ES. So our goal now is to solve for ES, and we can do that by factoring and moving the concentration enzyme substrate ES over to the left-hand side. So if we do that, then we're left with, on the left-hand side, concentration of ES times K1 times S plus K negative 1 plus K2 is equal to K1 times ET times S. So what we have here after factoring and moving ES to the left-hand side, we have, so I factored out ES times K1S, which is over here, K1 and S, and it's no longer negative because I moved it over to the left-hand side, plus K minus 1, which I also moved to the left-hand side, same thing with K2, and that's equal to K1 times ET times S. So now here we can divide this large value so that we can get ES by itself, and that is equal to K1 times ET times S over K1S plus K minus 1 plus K2. So from here, we can multiply by the reciprocal. Give me 1 sec here. 1 over K1 on the top, as well as the bottom, 1 over K1. So now, when we write out ES, that is equal to, these K1s cancel, so we have ET times S over S, because these cancel, plus K minus 1 plus K2 over K1, because the K1 doesn't cancel over here. So if you go back to the top portion of our equation here, you might notice something looks very familiar. This K minus 1 plus K2 over K1 is equal to this Km value. So I'm going to write that over here. We're going to come back to that later. Okay, so we know the concentration of the enzyme substrate, which is this value here. What if we want to solve for the instantaneous change in product over time? So we have here dP over dt, which is equal to K2 times enzyme substrate complex. So how did I get this value here? If you go back to the top equation over here, the instantaneous change of enzyme substrate complex over time is basically just looking for the reaction rate that is involved in forming the enzyme substrate complex. So down here, we only care about the formation of the product, and the only variable that's involved with that, if you go back to the very top over here, is K2 and the enzyme substrate complex, which is the substrate, because these two are the only things involved in forming the product. So now that we have this new equation here, we can plug this into here, or this into here. So once we do that, we can write a new equation. We can say velocity, which is equal to the reaction rate, which is this value here. This is equal to K2 times ET times S over S plus K sub M. So if you go back here to the top page again, you'll see that there's a new variable that we can plug in here as well. K2 times ET. That is equal to Vmax. This is Vmax. So what exactly is Vmax? So we have the total concentration of enzyme times the maximum number of molecules an enzyme can catalyze per second. Or in other words, the Vmax is equal to all enzyme reacting with the most molecules per second. And at that point, we have the maximum rate, or Vmax, again. So if we rewrite this, we have V is equal to Vmax times S over Km plus concentration of substrate. And this is the Michaelis-Menten equation itself. However, we have still yet to define what Km is. So Km is what's known as the Michaelis constant. So what if we allow Km to be equal to S? So we can rewrite such that, so let me box this here, as that is the Michaelis-Menten equation itself. V is equal to Vmax times S over concentration of S plus concentration of S, because they're both equal, or 2S. And the S's cancel, and we're left with V equals Vmax over 2. So what this basically is letting us know is that Km is equal to the concentration of substrate S at 1/2 the maximum velocity. Km will also tell us about the enzyme affinity with the substrate. If you have a low Km, meaning a small amount of substrate is needed to reach the half maximum velocity, then you have an increase in affinity for substrate and vice versa. If you have a high Km, or a large amount of substrate that's needed to reach half the maximum velocity, then you have a lower affinity for substrate. And that is the Michaelis-Menten equation derived. Thank you very much.